Yo, yo, yo! What's up, everybody? Welcome back. Today, we are working on our PNG loader again, attempting to get correct linearization of the data in a PNG. So the context here is we are trying to write an application, we're calling it Gamer ICC, which generates color correction profiles for a monitor that are lies in an attempt to make it so that when I play a video game, it's not so flippin' dark. Hold on, I need to change my monitor settings back to being correct because I actually have them on fuck my shit up mode when I play games. But okay, so I play a game and it might look something like this. I want to say, make it look like this, generate a profile so that my monitor will do that all the time. Obviously, this is like an extreme example, but we want to be able to basically like play around with parameters of this thing so that we can find something that we think looks good on a bunch of sample images and generate a profile. The problem is these samples that we're loading these are not right. This is not actually what it looks like because the pipeline to how these images got into this viewer are I play game, right? Play game. I record with OBS. Record OBS. And this gives me a little like MP4 or MKV file or something. I like extract frames with FFmpeg. FFmpeg. This gives me some PNGs. I then load the PNG onto the GPU. So with my app, so like app puts this into a GPU texture. And then this goes through like some more stuff that gets displayed on the screen, right? Now it turns out this part, fucking hard. It's just not trivial. It turns out that like the data that's in here, when we record with OBS, it records with some like color spec, right? Then FFmpeg respects that color spec and forwards that information into the PNG. And then we load the PNG, we get like the data, but the data is supposed to be transformed in some way because this guy wants linear data. And you might say, what are you fucking talking about? And kind of like the idea here is the way that you send pixels to your monitor is not necessarily the same way as it is mathematically represented in terms of like light energy, which is also different than the way that your eyes interpret differences in brightness. And so you have like values in this image that have RGB values, but they are not necessarily like what those RGB value means like depends on the context, right? And so what this PNG is saying in his headers is, hey, I have some RGB data, and everyone can agree on what linear space means, right? Linear space is literally like, what is the physical energy of this thing hitting your eyeball? I think so. I think. Relative to some like maximum energy, right? And so we need to basically like undo the transformation because they stored it in a different way because like maybe it makes sense to like allocate some of your bit depth to like the darks, right? So you kind of like use this nonlinear space so that you have more bit depth in the darks and the brights because like your human eyes will notice that thing more. Stuff like that. Anyways, so they define in here the white point that these things have, as well as R, G, and B like maximums, right? So like your computer can kind of only show like a certain amount of red thing, right? But in reality, there are things that could be like more red than that, right? Because like there's things that you will see that will stimulate the red cone in your eyeball more. So they kind of send us all of this stuff. They also, well, the PNG has a bunch of ways of displaying this, of transmitting this information, actually. Can we find that somewhere? Color spaces, maybe? Yeah. So they have many ways of transmitting this data. One of which is like the most advanced way is literally just giving you a color correction profile, which is the thing that we're generating, but like it has all sorts of stuff in there. Our PNGs don't have that. Our PNGs that we're looking at have CICP, chrm, and gamma. So CICP, ICCP is the color correction profile. CICP is like basically lookup tables into like this document, And we start like looking at like what this means, and it's like you have one byte that allocates transfer function. So what is the nonlinearity for this thing? What curve should you apply to this thing? And you look at this and you're like, oh, there's a bunch of like numbers in here. I don't really understand what they mean. And you might look at like an implementation of this thing. So we go into like MPV's code that has implementations for all of these tone reproduction curves, like colored TRC for this spec, gamma 2.0 is easy, right? You do power x2, easy. But a lot of these are not trivial, right? Like you look at this and you look at like color tone reproduction curve HLG. I don't really know what that means. But then you like see code like this, and I'm just like looking at this switch statement and I'm like, I don't want to do that, right? Like this seems miserable. I don't want to do this. So I've kind of said, fuck it. We won't support CICP. I don't want to deal with that. Maybe we will someday, or maybe we'll call it to some library. I don't give a fuck. But there are other mechanisms, right? So if we look at this like priority list, it's kind of like goes from like hardest to least hard to easiest to implement, but also like most complex to least complex, right? So we in RPNG have tags for gamma and chrm. So if we look at these guys maybe we can handle, right? So these kind of give us like the maximum red, green, and blue and white points. Because like if I look at a yellow piece of paper outside and a yellow piece of paper inside, my brain will still flag it as like a yellow piece of paper that's like the same yellow piece of paper. But the like measured energy coming off that thing is different because the light that is being provided to that is different. So we kind of specify like energy coordinates kind of relative to some white point, and we convert between these because like other file formats will be expecting like different white point references and different energies or whatever. And so we kind of want to convert to say like with this surrounding area, this is kind of how red this thing should look. And so we'll try to represent like that amount of red in a different space layer. And so they give us this. They also give us the gamma curve, which is easy, right? Just a power, easy peasy. So the interesting part here is mostly this chroma thing. And we've done like a little bit of research on this in the past. Basically, if you want to convert something that was measured at like different white points here, hold on. We can look up like D65 illuminant as an example. So the CIE, I think, which is some French color group, they define these like white points where you can kind of where was like the like animated GIF? Here. So like here we're seeing different standardized white points, and on the x-axis here you're seeing the wavelength of the light that was like the wavelength of the light that was being used to illuminate whatever you're looking at, and the y-axis is kind of like its intensity, right? So at certain color temperatures you're going to get like more of the lower wavelengths, but at certain temperatures you're going to get more of the higher wavelengths, right? And so are we trying to make a magic mushroom color filter? Yeah, I guess it's like about effectively the same. So if I understand correctly, the correct way to change between these white points is in perceptual cone space, which is also RGB, but it's a different RGB than you're kind of typically seeing in your like image files. So I think that like kind of the flow is something along the lines of you have some sort of like non-linear data where x-axis here is like luminance kind of. So like luminance kind of. There's like input luminance and this is like out value, right? So like, you know, if your thing was linear, it looks like this. This is kind of like more stuff is allocated to darks because you have the darks, like a short range of darks is mapping to like a large range of output darks, right? Type shit. Something like that. And so if you want to convert between these spaces, the first thing you do is you like linearize it, right? Which is done with the gamma curve they gave us. But now you're linear like according to some white point, right? So according to white point. And so you need to like go from this encoding of RGB values to some perceptual space where you're no longer measuring energy, but you're measuring kind of like activation of the human cones in the eyeballs, right? Which is not exactly the same. And so there's this guy, he made a matrix to do that. He has his name is Bradford. And he has some matrix where you take in some some value, some color value, go through his little box of things, and you get RGB values in LMS space, I believe is what they call it, where LMS is like the cones, your the 3 cones in your eyeballs. And in this space, you can just divide the numbers, right? So you go, all right, so I've got a white point of like 1, 2, 3, and yours was 0, 1, 2, or like whatever, like 0.6, 0.5, 0.7, or whatever. We'll just scale this like linearly and then go back to your old space. That's kind of like the way this works according to this page that we read at some point. From sRGB color space to sRGB profile, how to calculate the ICC sRGB profile primaries from the sRGB color space specifications. Right here, that's what this guy says, and I believe him. However, Bradford, he doesn't start from RGB. No. He starts from this color space called CIEXYZ. This color space is kind of like some like uninterpretable color space by a human, really, but like is kind of like pleasant for math, is my understanding. They kind of have like 3 values: capital X, capital Y, capital Z. Y is like a brightness, kind of. Z is like kind of blue, and then X is kind of like the rest. So like you can't really like look at this and think it like means something sane, but you can easily convert from these to other things, and it's like kind of like the common space that everybody works in. So Bradford takes an XYZ, you throw them through this, you get your thing back. Then when you want to go back to XYZ, you run it through the inverse of Bradford, you get back to XYZ. And so now all we have to do is figure out how to get from the color space that they give us in these XY white point numbers. I don't know what these mean yet. But figure out how to get from these to the common XYZ space. Once we figure that out, we can kind of implement like the white point adaptation, which we should be able to figure out. And then hopefully we'll be able to implement something that kind of works and we'll show an image that looks kind of right. Maybe? I don't fucking know, man. Oh, but that's the plan. That's the plan. So step 1 of this is figure out what the fuck these numbers are, right? Because if you look up like CIEXYZ, which is like kind of like the common color space or whatever, there's many color spaces. There is CIEXYZ, which is all capitals, and then I believe there is XYY as well, which is 2 lowercase xy and a y. And if I remember correctly from what we were reading, we should be able to, like, in XYZ space, X plus Y plus Z has to equal 1, so there might be a case where we're in XYZ space and they've dropped the Z because it's implicit. I believe XYY space, there isn't a value you can drop. But basically, I'm not really sure. And so what I want to do is I want to maybe start by looking at an sRGB encoded PNG. And then, since we have known values for sRGB primaries, we can kind of try to figure out what the fuck these numbers are, right? That'll give us some clues. So let's start there. And so can we, maybe, if I go in here and I'm just like, hit me with a new PNG, can I like save this thing and ask for it to be sRGB encoded? I hope so. Let's do that. Save. Okay. Not from here, but maybe from a more advanced image editor. GIMP. And if we can't do this, maybe we'll have to use some code somewhere. New. 256 by 256 image. And can we, you know, do a little paint bucket, paintbrush. He's happy. He's a happy boy. Export? What does this guy give us? Where do I want to go? Home, work, color adjustment, sRGB, hopefully, .png. And I believe he gives me options here. Right, okay. So we have compression level, pixel format. We can kind of force 8 bits per pixel RGBA. We have EXIF. Color profile is metadata. Okay, can we at least look at this guy and see what is said about him? How do we look at that? We have like our PNG processor somewhere. So maybe we can kind of use that as our starting point. sRGB, hopefully. Oh, nice. Our CRC validation is falling the fuck over. That's great. Comment 131. If true, return. Let's just turn that off for a second. Great. Great. This is just broken in general. That's so cool. Did we break this on everything? Surely this was working a second ago. Hold on. Res, PNG, res, smile, PNG. Okay, so it still works there, and then it also works on the other test image that we were working on. Samples, frame 91. Okay, so that's interesting. So whatever PNG we're generating is falling over in our guy, which is very fun. Why don't you use Neovite? Because I don't know what the fuck it is and I don't really care. I think you already have this intuition, but XYZ vector is both direction and magnitude. XYZ is normalized, not by Euclidean. You're talking about capital XYZ versus lowercase XYZ. But just x plus y plus z, so loss of the magnitude and is all direction. You can retrieve the full vector if you know the direction and one of the coordinates x, y, y. Makes sense. Makes sense. Someone saying that you can force it, you can use sRGB profile. Nice. So you're saying in GIMP, I can... Where the fuck is this? Image color management, use sRGB. Which we are doing. So I guess we can hope now. I guess the next thing to do is diagnose why we can't load this PNG in particular. Fuck. Unless we fucked up. Yeah, okay. Can we at least like log which sections we're looking at or something? Like, where is this falling over? Let's see. Where would this be? This is in process image. Can we at least log what we're looking at? Stood, debug, print, chunk. Where are we falling over? So we get to sRGB, gamma, chrome, fizz, and then we invalid CRC after reading the fizz section. So if we comment in consume outstanding. Oh, this is a bug. Here we need to self outstanding reader needs to equal none after we do this. This is just a bug where there's like invalid memory in there. Nice. Okay, easy. Easy peasy. Question, your goal is to get to 444, 422, 420 YCBCR space? I think I'm trying to get to linear sRGB. Pretty sure. But like not entirely sure. Okay, cool. So can we look at the gamma and chroma sections of this guy and figure out what's going on in there? So if we see more, I don't really give a fuck about. I guess if we see gamma, we are probably expecting to see like a 2.2 curve ish, right? What is in the gamma? What is in there? Gamma. Oops. It is 4 bytes as a gamma value encoded as gamma value times this. So we should be able to be like, take int, U32, big encoded, gamma val x, whatever it was, 100,000. Can we do a little float from int on this bad boy? And then can we do gamma is this, and we can do gamma val x 1000 over 100,000. We should put this inside the braces. Okay. So we see gamma of 0.45455, which is the sRGB gamma, which is promising. Okay, so now let's look at the fucking chroma tag. So if we see chroma, which is lowercase c or uppercase c? Lowercase c. If we see that, we are expecting 4 sets of 4-byte numbers. Each is the x or y value times 100,000. Did they throw in the sponge case gamma just for the lulz? I think that for some reason they want every leading letter to be lowercase followed by uppercase. It's probably like a little like quick validity check in some way, but I don't know. I just made that up. Okay. So we kind of do the same thing here, right? So if we see chrm, we kind of want to do like log x 10,000 number, 100,000 uint. Sure. And can we do like a std debug print of this number? Maybe x 1000 int as float, maybe? Maybe this is what we want. Return var ret is float from int of val. This is an f32. Return ret over 10,000. 1, 2, 3. Yeah. Okay. So then we can do, maybe we want to like turn this into like a read. So this takes in a reader. Like this, and then we get like r take int as a u32 big, try const ret is float from int on this, bang bang boom. All right, chilling. And then now we can kind of do read like this. This thing probably has to fail sometimes. Nice. And then we can go std debug print, and we can kind of just do this like this. Boom. And we go number, 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 number. Easy peasy. This guy gets turned into one of those nice little zig stringies like this. And then we kind of do this, and we just slap this in however many times. 1, 2, 3, 4, 5, 6, 7, 8. Boom. Okay. Am I fucking stupid and high? Hello? Gamma, Chrome, he just prints the gamma again. I see it right here. I made the change. Hello? Save? Oh, Zig build. That would do it. That would do it. Uh-huh. Okay. And then... Oh, we fucked up our unit test earlier, and I don't want to fix that right now, so we'll just comment that out. There we go. Okay. So, we have 6433, 36, and 156. Okay, this is really good. These are numbers I recognize. These are these numbers, wherever the fuck, I shouldn't have fucking resized the window, but these are these numbers, right? 6433, 36, 156. So these are the XY values of XYY. And is the Y white point 3127, 0.32. So now what's confusing here is like this value is lost, but is it like regainable somehow? Can we pull this back? Right? So we know the white point is 1.0. And is it like something related to like we have the white point? Not sure. Not sure. So can we, maybe we ask the idiot. Can I recover the Y value from an XYY without from an XYY value transmitted without the Y? Let's just see if he says something. No. Plus known S. What the fuck is S here? Didn't it have to do with that some operations are equal to 1.0? Yeah. We saw that. You're right. We saw that in this from sRGB color space to sRGB profile, how to calculate the ICC sRGB profile primaries from the sRGB color space specifications. We did see in here, he had something about like assumed Y value. Where was that? Here. Unadapted. So, okay, first of all, are these the right numbers? I lost it. 6433, 36, 0.156. Yes, okay. So, this guy was talking about before. You assume that these things are full luminance. Basically, you set 1.0 on all of these things. And then you create, what is this for? Unadapted red, green, blue from XYZ to XYY. Wait, is this the XYZ value? Is XYZ and XYY the same? Hold on. There's an XYZ to XYY conversion here. So, XYY to XYZ. Hold on. I'm also confused. These are uppercase XYZ here, but are there lowercase XYZ as well, or is he just fucking that up? Because I think I saw somewhere in the PNG specification, in the PNG spec, somewhere they link a color FAQ because, like, I'm a fucking idiot. And in here, kill me. Here we go. They talk about lowercase and uppercase somewhere. Pretty sure I saw it in here. When they start talking about, like, color spaces. This is not the thing I opened, by the way. This is a different... I could have sworn this is what I was reading before, but that does not look like... Oh, this. I was actually reading this. Color space conversions. This is what I was reading. So somewhere in here, they talk about case. Yeah. Lowercase is always used to signify chromaticity coordinates, and uppercase always signifies trisimultaneous values. So, like, my eyeballs versus, like, how color something is. Right? So I'm a little confused about this guy mixing case here. But we need to be sure. I mean, he's using lowercase here and then uppercase here. So I'm assuming this is just like a mistake. So he's also saying XYZ to XYY, which makes me think that this is XYZ space transmitted here. Maybe? Doesn't X plus Y plus Z equals 1? Yeah, I think I saw that somewhere. So that would make sense. That would make sense. So maybe they are transmitting... Can we... In here, he might talk about it a little bit. Yes, yes. Here he has the unadapted XYZ values of sRGB, and here he has XYZ. XYZ, XYZ, and these match the numbers that we see here, which is very good for us. Very good for us. Okay, cool. So, we have XYZ values without the Z in this color space that we don't really understand. But that's okay. So, he now talks about how to generate the matrix that converts RGB to XYZ in here. Because we are trying to go from sRGB with D65 white point. We are trying to go from there to ICC with D50 question mark? That doesn't sound quite right. We are trying to go from source color space unknown to sRGB with D65 white point. That's what we're trying to do. Where this happens to be already sRGB, which is very good for us. Because that means that after we do all this conversion, we should see an identity matrix, which will prove to us that we did the right thing. Mwah! Perfect. Okay. He's talking about something else, but we can kind of use the same concepts here, where he talks about basically you have Bradford, which uses the adapted XYZ values, I think. So there's this Bradford matrix, which we'll get to, but he converts to he does something to pull out some matrix. Oh, here. Yes. So hold on, I'm thinking. These are, so he has these XYY values. He figures out their like actual luminance values in some way. He has some conversion matrix where he fills in XYY, where capital Y is luminance, XY is chromaticities. He like rips an inverse matrix of that with the original white point, and that tells you the correct Y values for these things, right? So he finds these which match this based off of these. And so that gets us into CIE space. Okay. So then he talks about, to calculate these things, we go use Bradford transformation. We have the D65 to ICC D50 Bradford adaptation matrix from this. We use math to calculate XYY values. Then we get the XYZ values that are correct. Not in the like unadapted space, which I don't really know what that means. Then you convert to you use the Bradford adaptation matrix calculated in B4. Okay. So yes, okay. So the Bradford transformation matrix and its inverse are used to calculate a Bradford chromatic adaptation matrix from a given source white point to a given destination white point. And so they give us a matrix that converts us to LMS space. Yes. This sounds familiar. So we go from LMS space Then we go from CIE XYZ to LMS, I think. It's one of the many mathematical transforms suggested for converting XYZ to LMS. Yes. Okay. So we have some process. We have some process of going from RGB with white point to XYZ. This involves something that he describes down here, which is like take XY values with assumed Y, capital Y 1.0. Then calculate the in-term XYZ values, convert in-term XYY to XYZ, which gives us these. Invert matrix created from in-term XYZ, and then multiply white point. Then, like, multiply white point values, white point with inverted matrix. And this will give us the red, green, and blue components. Wait, what does this do? The third step is to multiply 3x3 matrix by the 1x3 in table 5D to produce the second 1x5 matrix. Is composed of the actual Y values. So this gives us Y values, RGB Y values for original XYY. Then we convert corrected XYY to XYZ, I think. And then that should give us something that resembles the sRGB matrix here. That should give us something that resembles this, right? Because I think we see that yeah. So he has this stuff, and then he converts them to XYZ, and these numbers match these numbers. Okay, cool. So we have some process to go from our color space to XYZ. Then we have Bradford matrix to convert from XYZ to LMS. We want to apply white point scaling in LMS space, then go back to RGB through XYZ, I think. Through sRGB XYZ to RGB, right? We're trying to go from some source color space to sRGB linear space. I'm pretty sure. That sounds right. So now we just have to do these two pieces. So let's try to figure that out. Okay. So at some point before now, we were looking at like a figure out set of transforms. So that's kind of ready to go. And now we can just kind of do them. And we can check if they're right because we have a sample to work with. Perfect. Okay, so let's go through this math. So we start with I guess we have to have some sort of like X, Y, Y value. Why did you choose LMS as your target color space? Because that's what this guy said to do in this blog post that we read at some point. And so we're just trusting him. And he says that that's what the ICC specification tells you to do. So like it seems kind of reasonable. But like that's what he says you have to do chromatic adaptation. So like I'm like, okay, if you say so. X is, can we work with floating points for now? I think that is easier. And so then our function, it takes in term x, y, y values, right? So it's like, this generates a matrix somewhere that we're trying to use, I think. Gen chromatic adaptation mat. Yes. And this is going to return I think we don't have this right here, but we have to get this thing. So we have like a math mat 3x3 is what comes out of this thing, I think. And we have interm x, interm y, and interm R, G, and B, and white point, I think is what they were talking about in here. Yeah, okay. Okay, cool. So let's start by, I think we need to find a build zig zon so that we have access to our math library. So name is image. He's got a fingerprint suggestion for me. Okay. What else is he mad about? Version. Okay. What else is he mad about? Paths. We got build zig zon. Is there a source folder? No. PNG zig, ppm zig, PNG. Probably that's most of it. Svimage zig. These are all part of our package. Okay, and then we have dependencies here. And we have math is, I think it's like this. I think it's like this. And then in our build zig, we like yoink that dependency and inject them in here. So we have math dep is B, add dependency math. I think it's something like this. And then we say like I guess for now this part doesn't matter. Exe add root module add import. Nice. And we say please take our math module, please, where we have matrix multiplication and stuff. Is he chill? Yes. Okay. So now let's just make sure this compiles. All right. I have no backup for this, but the LMS space makes some intuitive, naive sense. If you look at chromatic adaptation as a different cones weighting different inputs differently when sending signals to the brain, if you want to do the same weighting, we better do that in cone space, which is spelled LMS. I agree. I agree with that. I think that you're right. It is like kind of somewhat reasonable, and so when you see it, you're like, okay, if you say so. I agree. Okay. So, what the fuck did this guy do again? So we need to like in the chroma section read this thing, right? So can we interm from read interm, right? So he's gonna have a stud IO reader. He's gonna return an XYY value, right? And he's going to return X is try read X1000 as F32. Right? I think that makes sense. And we say 1.0 on Y forever. And then what does our white point look like? Because our white point also... Oh, white point has known 1.0 luminance because your white point is the brightest you could be, so you're chilling. Got it. So now we can kind of do this where we say... read interm on the reader And we can say this is the white W RGB. And we can use this to call our matrix. So RGBW. Chrom adapt mat. There we go. Easy. Okay. Oh. We'll use WT for white because it conflicts with the name somewhere. Okay. So now he crashes because he's like, I don't know if I can know how to do that yet. And we're like, that's fair. Okay, so we have the steps. Takes XY values with assume 1.0. Done. Done. Convert to XYZ. So what is the XYY to XYZ formula? This. Okay. X is X times Y over Y. So can we do this? XYZ. And we can say function from XYY. In is an XYY. And we return XYZ. Okay. And what is he pissed about? No semicolon there. Okay, so we go return X is in X times in Y over in Y. We got Y is in Y. Beautiful. We have Z is 1 minus in X minus in Y times in Y capital over in Y. All right. So we should be able to do like std debug print XYZ from XYY in term R or something. And this should match what the guy in the blog said. So we get 1.93, 0.33, 0.09. And is that what this guy has? Wherever the fuck. Wait, where was it? Here we go. 1.9, 1.0. 1.93. Y 1.0 on all of these. Z 0.9. Oh. Big Y, not little y. Okay, that seems right. And then we do the same thing for green and blue. And make sure that we see the same thing he sees. So 0.51, 0.16, 0.51, 0.16, 2.51, 0.13, 2.51, 13. Chillin'. Okay. So then he converts this stuff into a matrix and inverts it. So here you want each column in the matrix is one of the colors. So here we have in mat, or so like interm mat is a smath mat 3x3. And can we generate these easily? I think that we just literally fill the data field manually is how we work with this thing. So we want interm XYZ is this. Yep. Interm green, interm blue, which comes from green and blue. Okay. In the vector direction, magnitude intuition, y over y is the reconstructed magnitude. I don't really know what the fuck is y. Like the lowercase x, y lowercase is like chroma coordinates and y is luminance. I don't really understand why y is being used as our magnitude here. You know what I mean? Like that doesn't really make sense to me, but I must not be understanding something. My intuition is lost now. So we want IR XYZ X, IR IG XYZ X, and IB XYZ X, I think. Because I think that we want all the reds to be in one column, and all the greens to be in one column, and all the blues to be in one column. Oopsies. I think. And then they're saying that we should be able to invert this matrix. So we should be able to be like inter mat invert, which thank God we have. And then we should be able to log this. Okay. So this gives us 0.689, negative 0.326, negative 0.106, negative 0.6893, 1.34, 0.02. So we're chilling. We are big chilling. Y divided by y is the magnitude. It makes sense if you look at the xyz as an arbitrary geometrical vector and the xyz is the normalized version of it. Ah, I see. Yes. Yes, I think that makes sense. Yeah. So y is y over y because you're trying to normalize, like unnormalize or normalize one direction. That makes sense. That makes sense. Okay, so we have this inverse matrix this guy's talking about. And so now we're like trying to take their white point and convert it. So their white point is with 1.0, and we just then convert. Oh, we need to convert this to XYZ as well. So we have white point XYZ is XYZ from XYY with the white point. Cool. And I think he's saying we just rip that shit through, right? Yeah, and this gives us the new Y values. Or like the unadapted Y values or the adapted Y values? Actual unadapted Y values. Actual Y's is going to be this multiplied by our vector, which is like this, XYZY, white point Z, and this gives us the actual Y's. So can we print in actual Y's here and see what we get? We did discard this thing for no reason now. Hype, so we get 217107, 217107, beautiful. Right, so now we have the XYY values of these things. And so we can kind of say like actual R XYZ is going to be XYZ from XYY of interm R. Hold on. Interm RX. We use Y from these, and we use our Y from actual Y0. And we should be able to do this for G and B as well. So this is GG1, B2. And we should be able to actual R, XYZ, we should be able to log these guys and see that these match what this guy calculated. 412119. Perfect. And I believe now these should actually match the sRGB matrix from Wikipedia. 4121019. Beautiful. 357111. 357111. Beautiful. 180795. 180795. Beautiful. So now we have any arbitrary RGB to XYZ generation, right? So this is going to actually be called gen RGB to XYZ mat. So that's what this guy returns. So we just have to return it's the columns, right? R412101, yeah. So this is actual RXYZ.X, actual GXYZX, actual BXYZX, boom, and now YZ, 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 beautiful, and this is a mat 3x3, so this is actually the data inside this thing. All right, okay, cool. So then, when we want to generate this matrix now, we now need the Bradford matrix, which we should have somewhere. Bradford. Maybe in here. Maybe here. Bradford color matrix. I think it's in that blog post, but I want like a second source as well. Yeah, so it's this guy. 0.8951, 0.2664, blah, blah, blah. And then in this blog post, when he talks about Bradford, is it the same one? 0.8951, 0.2664, 0.1614. Yeah, okay. So these are the same matrix. So here we should be able to be like, Bradford is a SMATH mat 3x3, and we have data with these constants. 0.89, here, we'll do this. 8951, 0.2664, negative 0.1614. Why am I copy pasting? Negative 0.7502, 1.7135, 0.0367. Beautiful. 0.0389, negative 0.0685. 1.296. There's an 0296. Perfect. I think that's right. And so I guess, can we also do inv Bradford? Is Bradford inv? Like, is that going to let me do that at compile time? That's kind of sick. And so if we're trying to gen the chromatic adaptation matrix now, we are going to, this is always going to sRGB. Always to sRGB D65 illuminant. So this guy's going to take in the info we get from the PNG, which is this stuff, and he's going to call gen RGB to XYZ mat for this stuff, because XYZ format has a defined white point. Am I missing something in here? Oh, this is without the color adaptation, right? So we have the matrix here. Yeah. Okay, cool. So we go gen RGB to XYZ mat of all this stuff. Input to XYZ. Then we combine this with Bradford. So this is input to LMS. We want to apply a scale, so we want to do like a scale. Okay. We don't have like a nice little thing for this, but we can make one. But whatever, we could say like white point scale. So we use the LMS white point. What does he say? Somewhere. he talks about the scaling part. Where is that? Oh, he doesn't give the exact math, but we did this the other day in like a Python script that we tested somewhere. I don't know which one. This one probably. Uh, yeah, here. So we have the white points of the input, which should be 0.95, 1.0, 1.08. Is that what we see in our sRGB profile? And then we have the destination, and we put that as a scale matrix. And so we need these values as our destination. Yes. So we are looking for sRGB white point RGB, or LMS, I guess, is 95047. 95047. Something like this. I'm not really sure yet. 1.0 for green and 1.08883 for blue. And so our scale is going to be like we need the sRGB white point. We have that. So we need their white point in RGB. So I guess we do input white point RGB, or LMS, is going to be input to LMS multiplied with 111, I guess. Right? Because this will give us like the brightest value that they can. That should create the white point. Who would have thought that image rendering manipulation is so hard? Holy smokes. Yeah, I agree. Isn't this fucking crazy? Isn't this insane? Let's just print this and see what happens. Because I'm not 100% sure about these. So we have I guess input white point LMS, and then we sRGB. Comment this one out for a second. Gen chromatic adaptation matrix. Matte. Fine. Oh my god. Gen chromatic adaptation matte? There we go. So we are getting these numbers, which should be very close to the sRGB ones, right? Well, that's not good. This is not right, I don't think. I don't think. What is this matrix again? Oh no, sorry. This is an LMS space, which should match what we had in our test thing. Here we go. No. Which of these, like, fucking... Test 3 looks relevant. 95118. These are in what space? D65 white point. Like, what are these numbers? We need Oh my god. Just give me the numbers. What do these represent? Are these XYZ? These must be XYZ because we're multiplying by the Bradford matrix in this test that we did. So if these are XYZ, then we want input to XYZ here should be a number that we recognize. If this is the right space. 951.1.08. Wait, that's good. That's good. That's a number that we recognize. 951.1.08. Perfect. Okay, so this is sRGB waypoint XYZ, and this is the input waypoint XYZ, and these are like approximately equal. Cool. So then, now that we have these, it should be easy to do something, right? We convert these to LMS both. So we have sRGB waypoint LMS is input is Bradford matmul sRGB waypoint XYZ. Perfect. We have the input waypoint LMS is input to LMS multiplied with 111. Okay, this would be mul. Oops. Cool. And then can we print? These should still be the same. If we got this right, these should still be about equal. Input. Yes. And this should be LMS both. Okay. So these are, in fact, the same fucking number enough. They're like close, right? They're almost exactly the same. Okay, cool. So now we just make our scale matrix, which is a 3x3 matrix where the diagonals are the XYZ fields. So we are trying to get to sRGB. So if we're trying to get to sRGB, it's on the bottom, on the top. We have a value. We have max sRGB over max input times input. So if the input cancels out, if the input is max, then the max inputs cancel out, we get sRGB. Yes. So this is like this. And then a couple zeros because we're trying to write down the diagonal. Throw some 1s and 2s on these and then rearrange them like this. Beautiful. Beautiful. Okay. So then we apply the scale in LMS space. So we have input, we have scale mat applied after input to LMS, right? So this is scaled LMS, input to scaled LMS. And then we just go back the other way. So we go, XYZ to sRGB is a matrix that we have known. So we have this sRGB matrix. So sRGB to XYZ, we can copy from Wikipedia. Right, so this is 0.4124, 0.3576, 0.1805. Oh my lord. 0.7152, 0.0722. And for the record, also, we're doing like the stupid people version of the PNG conversion, right? We're not even attempting the hard version, which is very funny. sRGB to, or yeah, XYZ to sRGB, I guess, is going to be sRGB to XYZ inverted. Cool. So now we have that, and we just have to do LMS to XYZ, right? Which is inverse of Bradford. So we have inverse of Bradford matmul with our shit. And this is matmuled with XYZ to sRGB. And we return this. But before we do that, we log it. And I think that we're hoping that this is like an identity matrix. I think we are hoping that this is almost identity, which means that like almost nothing happened. Invalid format string ret. Oh yeah. So true. And this is very close to identity, right? If we were to round these to like the nearest 4 decimals, I think that this would become ones on the diagonal, right? We have almost 1, almost 0, almost 0. Almost 0, almost 1, almost 0. Almost 0, almost 0, almost 1. I think the numerator and denominators are backwards there, but very much not sure. You want to expand to multiply by the old white point and normalize to divide by the new white point? I was thinking that I'm trying to get it... Like, if you multiply old by old, you're getting like old squared over new. And I would have thought that you want olds canceling out and to get new. That's what I would have thought, right? If I'm saying like my white point of 1, 2, 3 should map to 7, 8, 9. You want like 7 times 1 over 1 to get the 7, right? And like 8 times 2 over 2. And 9 times 3 over 3. That's my understanding, which makes me think that you have new over old, which is I think what I did. sRGB over input. But maybe I'm like completely misunderstanding like the point of this thing. Except if you think of the white point not as a value, but an inverse value. Yeah, okay, we can double check. I mean, the fact that we have... Oh, I guess here we have an identity matrix would still be true if we got it backwards. Okay, let's look at what this guy says. What we can do is we can use the D50 white point as our thing, and then see if we get the same matrix that he does at the end. Let's do that, because that'll make it clear. So what is the D50 white point? D50. Here. This is the D50 white point. Okay, so if we do this instead, we should end up in... Oh, but this is wrong actually because we're doing the sRGB calculation at the end. So we want D50 white point XYZ. We want to just do a test here where we go Bradford. We want D50 white point LMS here. And then can we apply a scale mat with D50? And then we should have everywhere that says sRGB here. We have this. And then we want to print out the in Bradford matmul with scale mat D50 matmuled with input to LMS. Maybe just the maybe just Bradford. Yeah. So this should be like D50 adapt is this part of the transformation. And then we should be able to print D50 here. And then we get 1.04, 0.22, and he says somewhere down here 1.04, 0.22, negative 0.05, 0.29, 0.99, negative 0.01. So my understanding of this problem gives me his chromatic adaptation matrix, which I think means that it's the correct order, like the correct inversion. But it was a good thing to bring up either way. I'm glad that we double checked. But I'm pretty sure this is right. Pretty sure. So now we have this chromatic adaptation met. I can't argue with the data. Well, we don't. That blog post, I don't know like how trustworthy it is. It's just like a guy that we saw on the internet where we ran through the steps and got like the same answer at the end. But like it feels kind of right. Can't argue with the data though. Yeah, it feels. Sure. Okay, so now we have this matrix, and we have a gamma. So I guess what we should do is we should get the gamma value and the chromatic adaptation mat. And maybe we have this as, we put these as both like 3x3 matrices for a second. So I guess we've kind of done this. And that was at some point before now. So now we're trying to apply these to some image before we write it out. Perfect. We can do that. Okay. So we pull out the gamma, we pull out the chromatic adaptation matrix, and so gamma here is just like gamma is equal to read this. Cool. And chromatic adaptation matrix is this thing, so we assign this as here. And then as we like go pixel by pixel, we have to like apply these things in inverse order. So I believe it is we want to linearize first, then apply the matrix. I'm pretty sure. Because the matrix is applied in linear space. Yes, so it has to be. Okay. So we have a pixel, and we want to say pxr is studmath how x the r value to inverse of gamma, or with the gamma applied. R value is R gamma value is 0.454545. So I believe that you have sorry, I have to draw it to figure it out. This is like what the monitor does. This is x to the 2.2. So if you have the inverse of this is x to the 0.45. If you want to linearize this, you apply the inverse of this. Yeah, so you go 1 over gamma. Okay. Beautiful. And then we apply chromatic adaptation. So we say chrom adapt mat mul r g b. This is the adapted. And then we should be able to do px r is adapted 0, gb 1, 2. And if we run process image on our test case, samples frame 9.1, to test ppm. He's mad because we don't have our types specified here. This RGB is also mad, interestingly. So we need RGB vec is going to be a 3 floating point numbers. So this is going to be float from int R, G, and B, but these are in this range of 0 to 255, so we want to do 255 here. And then I believe now we're chilling here. So actually we can probably do like RGB vec is equal to std math pow, and I think we can actually just shove this right in here. And I believe that will do a nice little thing for us. Does this thing have to be floating point, or can this guy be a vector type? I hope it can be vectored. Oopsies. And then we have adapted is RGB vec, and then here we need to do int from float on all of these guys and times 255. And then we probably clamp this. Right, something like this. Something like this. Fuck it. How we did forget to put the gamma part in here. Splat that fucker. In case you can correct my intuition, if you say I have a very red white point, I interpret that to mean that red things look white. Say you look at an object of that color, energy hitting the eye sensor is 1.211, which is then divided by 1.211 to yield 111. So to get the adapted back to the LMS energy, you multiply by 1.211, then you multiply that energy to some new white point, you divide by it. Oh, okay. I agree with the part you started with. I agree that my understanding is that the white point, if it's very red, red looks white. I think. The rest, I'm getting lost on. So you take an object of that color energy, hitting the eye sensor. The white points are defined in perceptual space, which is confusing. But sure, let's say that you've defined this white point in perceptual space. And that white point is emitting a spectral distribution of wavelengths that hit this paper and bounce back into your eyeball or fucking something, right? So you get the same value of the light back, and you need to normalize that to 111. And so when you want to go back, you multiply. Then we want to adapt that energy to some new white point, you divide by it. Okay, I see what you're saying. I think that the only mismatch in expectation is the conversion part at the end. Right? I'm not sure if this conflicts with what you're saying, but my mental model is that we have some RGB value 111 associated with some cone activation in my eyeballs, right? And that cone activation is only true if I'm under that red light. And we are trying to convert that to a similar perception under a different light, right? So we're saying, what are the new cone activations that have to happen under the blue light to make the thing look as look white, right? So we had a red paper under the red light, it looks white. We have a blue paper under a blue light, that looks white, right? And so I guess it's kind of saying like, you need to convert the red to the blue. That's how I visualize, that's how I think about it, which means multiply old value, divide old value by old point, multiply by new point. Right? I think that makes the divisions make sense. Right? So to get from red, to take the most red thing you have and turn it into a blue thing, you divide by red to make 1.0 everywhere, and then you multiply that by blue to get blue everywhere. You know what I mean? I think that makes the scale make sense. I think. Oh, POW doesn't work for Vec 3 here. All right. 1 over gamma. So I guess it's like this. That feels kind of right. All right, let's see what we fucking get here. It's pitch fucking black, but the good news is I think that might actually be right. Hold on. Frame 091. Oh, you mean MPV installed. Dance, ha, bum, 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 bum. Okay, so no. That is not right. Fuck. Fuck. Wait, can we compare to what we were doing before? So let's turn off the chromatic adaptation and gamma application. If false. Because I'm pretty sure this looked wrong before. Okay. Right, so oh, you know what? Maybe this MPV isn't doing the conversion until we apply a profile. Yeah, it could be something like that. Hold on. What the fuck? What the fuck, what the fuck, what the fuck? Let's not do the chromatic adaptation. Let's only apply gamma. Oh, wait. Oh, wait, hold on. Is it still if false? If true. Let's do the application. Yeah, so interesting. Interesting. Maybe the ppm is expected to be an not linear space. That's very possible. ppm linear. ppm image format. However, depending on the application, the use color space can be sRGB or linear. There's no metadata to indicate which color space is being used. Okay, fuck, that's annoying. That means what? We compare, I guess. I just want to double check now the ppm thing that we open here. So if we open our GUI, which right now is doing none of this shit. Do these look... Oh, fuck. Hold on. What am I trying to do? I don't really know what I'm even trying to compare. I guess I'm trying to compare no changes, just give me the data directly read out to a ppm. And compare that to what I see when I run my GUI and render stuff with OpenGL. I guess that's what I'm trying to compare. And I believe I actually don't know what to think about that. Because our OpenGL version of this thing is literally interpreting the data as linear. So is the PPM. Both of these are interpreting this as linear, I'm pretty sure. In which case, MPV. Oh, hold on. Okay, let's do this. Let's do this. I actually think maybe what we're supposed to do is apply the chromatic adaptation and then put us back in sRGB curve space. Yeah, I wouldn't be surprised if it's something like this. Where it's like we do the chromatic adaptation and we're supposed to apply the gamma again. It might be something like that. Like we do the transformation in linear space and then we go back. Does that make us look a little bit more like what MPV gives us? Let's check. Okay. And then can we MPV this? No, this is clearly wrong. Right? This is clearly fucking wrong. What language or framework are you using? Basically none. Like effectively none for anything that we're doing. We've kind of loaded everything from scratch. He's speaking Canadian. Huh. Interesting. I don't know what we've done wrong here. I mean, it's clear that exporting the linear version of the image in a PPM file feels wrong, right? So it makes sense to me that we bring it back, we apply the gamma again to bring it back to the original sRGB space. Like, okay, so if we do this, by the way, nothing should change, right? Like, that should look like a normal image. Right. So it's by applying the chromatic adaptation matrix, which, by the way, should be approximately 1, right? Can we just double check this? This should be effectively like, these are very small. This is, yeah, this is effectively identity, right? So given that we're having an effective identity matrix, it's crazy to me that doing this is changing anything significant. But we're seeing like some artifacts here, probably just due to like numerical inaccuracy. I guess. Yeah, that's very strange. Very strange. I mean, it's clear that this matrix is not perfect. Maybe if we do the clamping before? Can we do like something like this? Like do this like this, and then the clamp here doesn't have to exist, and we can kind of just assume that the numbers are normalized correctly by this point. Splat must have a no result type. Oh. I don't know, man. I don't know. as vec3. Is he happier if I do that? Yes. And then does it look less like shit? Okay, that's good news. We lose. Okay, that's good. And then does this look like MPV? No. Does it look more like MPV is the question, right? So we can have this on. So we're going to say move test ppm adapted. And then we're going to run it again with none of this processing happening. And so we have test ppm. Okay, we should have adapted ppm. So what is the difference between these? When we apply our chromatic adaptation, test, adapted, test, adapted. The adapted one is like kind of darker. And then what does MPV look like relative to the test image? MPV makes it look kind of like slightly more like red. And like not really any, maybe brighter, which is interesting. Which is interesting. Oh, right. I forgot that the matrix is not identity on this image. On this image, it's fucked up. I forgot. You know what we could do? We could try flipping this to see if maybe like we've messed something up. I'm curious to see if we flip this, if we get something that resembles more correct, because that would bring back Mr. Kernerston's way of thinking about it and make it kind of like more, like if it matches more correctly, then maybe he was right the whole time and our like little tests were not. So can we close all these things? We ran it with this stuff enabled. And we should be able to open this guy and open MPV again. It's interesting that neither direction is correct. So here ours is like too bland, kind of. But I think it was the same the other way. Yeah, it's kind of like the same. Although this kind of looks more correct than the other way. Hold on. I can't remember where we were anymore. Oh, if false. We should probably have this on. Hold on, was that test done with if false? Because if so, we need to do it again. Input. sRGB. So this is, hold on. Let's actually make some names for these things, 'cause I'm fucking lost. So this is move test ppm. This is inverted scale. Okay. And then I think it should be sRGB over, but that wasn't really producing what we thought. Okay. So can we like move test ppm to my way? And then let's do if false here. And we'll call this move test ppm unfiltered. or something. I guess also we know that many image viewers like presented these images differently. So I'd be curious to see like how XGG open of this thing compares with all three of ours. Holy fucking balls. What the fuck are they doing? That's fucked up. It's like so red looking. Okay. Unfiltered ppm. Okay. So this is what Gwenview thinks it should look like. This is what ours looks like by default. My way versus unfiltered. So fuck. We need another comparison. XGG open unfiltered. Okay. So this is what the data looks like with no filtering. These are both unfiltered. So my way, it kind of makes things a little less red, right? A little less red, which kind of implies that inverted scale, it also looks less red. I don't really understand. So my way versus inverted scale. I actually like can barely tell the difference, which is interesting. I guess we did see that the matrix was almost identity. Can we log the white point of this thing again? Is it just that the white point of this thing when he's using chroma and gamma are like almost null? Or is it like the same? Hold on. This is W. Hold on. RGB. Right, because originally we were doing this test with an actual sRGB image, which this should not be anymore, I think. Not really sure. White RGB. It's going to be very funny if we get through all this and this is just an sRGB image from the fucking start. Can we look at okay, compare this with hopeful sRGB. What was it? There was like a hopefully sRGB image somewhere. Yeah, this guy. Fuck, that's funny. Fuck, that's so funny. The thing that we had was just actually encoded as an sRGB image when we use this gamma and chrome thing. So there should be no difference because it should be identity. Fuck. So any difference in behavior here is trying to use the more advanced fuck, that's funny. So the image that FFmpeg exported gave us basically a sRGB gamma and chroma tag, but it gives us something different for the ICP stuff. So in terms of like the like levels of correctness, it's like doing nothing was almost correct, which is very funny. So we did all of this work today to do chromatic adaptation to see zero effect on our sample image. Fuck, that's funny. But I think it's still exciting that we have a chromatic adaptation thing that does nothing on an sRGB image. Almost nothing. It's like pretty close to correct. And all of this was to see, I guess, if these like low res tags would give us the right answer. And I guess the answer is that they don't somehow, which is very interesting. So we have to decide what to do about this next. It's still very confusing that MPV shows something different than us. Yeah, all of this is just kind of confusing. So I'm going to run some experiments, figure out what the fuck is going on, see if we can get a more accurate preview in MPV. Or sorry, in our GUI app. And we'll see what happens. Cool. Well, I mean, at the very least, we didn't make things worse. Let's fucking go. Thanks for watching, guys. If you like what we saw, we stream most days. We aim for 12:30 to 4 Pacific time. It's 4 Pacific time now if you're watching live, so anywhere between 3.5 hours ago and now is when you should expect to see us. There's a YouTube, there's a Twitch, there's a Patreon. If you pay in any of those places, you get access to VODs of the stuff that we don't post on the normal YouTube. We do that because like sometimes I'm not posting something that's like well structured and well thought out, and there's like more stuff that makes sense to post to YouTube in a day, and also like the stuff that we post to the Patreon and stuff, it's like, how do I say this? It's less stressful to me because that stuff can be less structured. We can kind of just go wherever the day takes us. So if you want access to those VODs, consider supporting. It makes it so this can continue longer. I make about 1/10 of what I made as like being a real software dev. So it's not sustainable, but every dollar I make makes it more sustainable. So yeah, thanks for watching. YouTube, peace out, and Twitch, let's find someone to raid.